My favorite word what you did was we had sketches
Okay, I don't have a temperature.
It's average long, so it says like
Huh? Cannot answer for my students.
I just wondering if they're.
Did anybody respond to the sound check? And people online, hear me?
No, there is no feedback. There's no echo.
There's no, okay, let's play the old game with changing.
Oh, yeah. That's okay.
Oh. The robot. So now it's.
I said it twice. It's equal 10 times.
So let's start off. Look at this. We're actually starting a minute early, which means I can go late. Any questions before I go over these announcements from last time? Type them in, yell at me. So there's an exam coming up. What is it? Is that 2 Fridays from now? Yes, 2 Fridays from now. It will probably include all the material up to maybe the Monday before that test. Just to let you know. And just to get you looking forward, just before you leave here in November, we'll have another exam. That second exam should be November 13th, not the 18th. But I'll check that one. I don't know if that date's correct because November 20th is a Friday. So I think it's November 13th is the second exam. And then the final exam is actually scheduled, the date and time, before the semester even starts. And it goes back to when all courses were scheduled. They developed this master schedule of exams. They trying to minimize multiple exams on any given day for all the students. So that schedule has been around for decades, time immemorial. But again, if you have any issues with the exam date or time, you need to let me know well ahead of time so we can try to negotiate how we're going to do it. But coming to me the day before and say, I can't come because I've got a hangnail that day. There's not much I can do at that point. I can't find extra rooms, can't find extra proctors, etc. Lab 3 was posted today, as you saw, during the week. That announcement is on Blackboard with Canvas. And again, as always, expected. So any chat room questions? So we were talking about forces on plane submerged surfaces. This thing is always in the way. And so we theoretically developed the force on a plane submerged surface. That's pretty straightforward now. And really, after all the differential calculus we did, that's a pretty simple result to do. All you need to do is find out where the center of area is for your object. Once you know that, you need to find the pressure at that location, multiplied by the area of the magnitude of force. The more challenging one is figuring out where the force acts. And again, for that, because we're working in this X, which is a horizontal surface that's on a free surface, and Y, which is an inclined axis, since we're working in that plane, we need to have a coordinate XCP, YCP to locate where this force is acting. And so the the force along the y-axis is a fairly straightforward equation. YCP, which is the location from the free surface to the center of pressure now, is a sum of the distance along the y-axis to the center of area, plus some term that's a function of two of the properties of the area, the moment of inertia of the centroid and the area itself. And then the last term is the depth of submergence of the center of area. And again, in that first term, IG over Y bar A, the only thing that really changes on a surface is the depth of submergence. And so physically what it's saying is, as the depth of submergence of your area gets deeper and deeper and deeper, its Y bar gets larger and larger and larger, the center of pressure is moving towards the center of area. And then the other direction, if we have a figure through which we can put a y-axis, which happens to be an axis of symmetry, then we know that the center of pressure dimension x will be right along that axis of symmetry. And so typically, for example, for a rectangle or a circle, where the axis of symmetry is right down through the center of area in either of these cases, the force is going to act directly below the center of area, YCP. So that's everything we developed. And the last thing I might identify is, and I'll show this on another slide, this equation, force is equal to PGA, is basically another concept. It's just the volume of the pressure prism that sits on the surface. So I'll sketch that on another slide. And as such, this prism, which is a linearly changing pressure as you move over the surface, the force is going to act through the central pressure prism, which is XCP and YCP. It's not saying anything different. It's just another way of looking at it. And another thing I want to get into today is force confidence. So obviously, we can put everything into a vertical and horizontal plane, even though we have this inclined surface. That's what I'm going to talk about. So at the very end of the last class, one thing I stressed is we're going to have these surfaces. So we looked at first at a vertical bulkhead gate. And first we said it was rails that was holding it in place. And in this case, the force of the fluid, F, on the surface has to be offset by the resisting forces of, in this case, the rails on that force, the fluid force. And so the rails would maybe split that force, and each rail would be applying half of that force, such that the sum of the forces in this horizontal direction are zero. You could also just hold the gate at the bottom. So in this case, I'm pushing in this direction, and I not only have a moment at the bottom, but you need to also have a force resisting the force. So this is a static equilibrium system. It must subscribe to force equilibrium and moment equilibrium. And both of those say that either the sum of the forces in any direction is zero, or the sum of the moments at any point in space. When thinking about just this system, the sum of the moments is zero. They cannot hear me?
They said it's fuzzy.
It's fuzzy. It's buzzing?
Fuzzy.
Fuzzy. And let's see if I change this. Does that help at all? Does that make the sound any better? How about that? Is that any better? Let me know by chat.
They said
Yeah,
yes, it's better.
Yes, it's better. I may not be able to improve how I look, but I can improve how I sound. So, again, we can have resisting moments at the base to offset that force. Once we talk about moment equilibrium, we need to know moment velocity. And also, whenever we have a pin connection, there are always forces that are acting in the pin. Think of the hinges on a door. There are forces at moments which will act as hinges of the door to maintain equilibrium. So I want to do another example, kind of similar to the example we did last time. Before we had a vertical gate, now we're going to look at an inclined gate. And we're going to ask a lot of different questions, but also expand this into compounds. So what we're going to have is a system where this again is in the way. So we're going to have a system where you have this gate, and this gate is 8 feet along the inclination angle. And it's, as you can see in the problem statement at the very top, the gate is 6 feet of width into the board or into the paper. If we look at the distance of submergence from the free surface down to the top of this 8-foot by 6-foot gate, we have 18 feet along the y-axis. And again, if you want to convert any distance L along the y-axis to either a vertical or a horizontal distance, I've given you those equations. So for example, H is equal to L sine theta, which just means that L is equal to H over sine theta. So for example, if we have 18 feet along the inclined axis, the 9 feet is the 18 feet sine of 30 degrees. Sine of 30 is 0.5, 18 times 0.5 is 9. So again, we can convert any distance between the h-axis, which is vertical, and the y-axis, which is inclined. And if this is our surface, so all I did was highlight it in red. That's our surface. This is what it looks like. This is the next slide. So again, what this surface looks like, when you look down, right down on it, it's 8 feet along the inclined axis. It's 6 feet into and out of the board. And it has a center of area, as you would expect, right in the center. So either go, oops, I can go back. Either go 3 feet from either side, or 4 feet from the top. So again, that's what the gate looks like. And what we're trying to do, if the top of this gate along the y-axis is 18 feet along the y-axis to the free surface, or 9 feet vertically to the free surface, we could calculate the pressure at the very top. Again, we can calculate the pressure at the very bottom. But more importantly, remember, all we need to do is calculate the pressure at the center area. And we know where the center of area is. And that will give us our force. So this is a plane submerged surface, the gate. Fluids on one side of the surface, which is really common. There are problems, either I'll throw at you or the FE exam will throw at you, where you have different levels of water on each side. And you just break it into looking at the left side, looking at the right side. The gate and the fluid are static. These are static equilibrium problems. So fluid statics applies. Once we move into fluids moving, fluid statics does not necessarily apply anymore. Okay. Some of the forces is not zero, some of the forces is mass times acceleration. That's when we get into momentum in this course. many of your design problems will be static equilibrium forces. That's why I'm spending all this time. So here are our fluid statics equations. And again, some of the forces in any direction for this will be zero. Some of the moments in any direction are going to be zero. And those moments can be taken anywhere in space. Your real challenge is calculating the moment arm to the point in space you selected. And again, the wisest thing you can do is always pick a point where one or more forces are acting first, because then their moment arms are zero. They just fall out of the equation. That's really the key to really running equilibrium. So, as I've instructed you before, and I'm doing it again here, when you have a problem given to you like this, the best thing to do is start off with a three-body diagram. And that really helps you visualize them or set up the force or moment equilibrium equations. So in this case, here's the gate between A and B. And remember, what this problem is after is the reaction force at A. So this gate is just resting at A. And there is a reaction force at A. The pressure distribution on one side is what's driving this reaction at A. However, if this gate had a weight, that would also be complicated. So again, in this problem, you're to assume the gate has no weight. But in many problems, you will see that the gate has weight. And that just is one more force or one more moment you have to deal with. Recognize that. Most problems will either tell you the gate is weightless, or they ignore it, or they will give you the weight of the gate. And typically, if it's a uniform material, that weight is going to act through the center of area of the gate. If it's a non-uniform material, you got to figure out where that weight comes. So this is our free body diagram, and we can certainly look at. Let me see if I So we can certainly look at this problem. So we have a pin connection at D. And we can certainly say that the sum of the forces in the x direction to the right being positive is equal to zero. You could certainly start there. And if we did that, again, what we're after is RA. So we would look at all the forces and you would see RA has no component in the x direction. Now, maybe doing this analysis of all the forces in the x direction will help you find out some of the forces you don't know, so you can find RA. If we expanded this you would see is the weight of the fluid, the pressure distribution of the fluid on the gate would have a component in the positive x direction. The reaction force at the hinge would be in the negative direction. And those are the only force components that are in the x direction. In the, if we want to call it the z direction, which is positive upwards, we've got this component of the fluid force acting in the negative z, and we've assumed that we've got this component at the hinge at B in the negative z, and then we also have RA. So in this case, again, some of the forces in the z is zero because the gate's not moving, sitting still. And that would equal, for example, RA minus the fluid force component in the z direction. This is one reason why I'll talk about fluid components next, minus FZ. And yes, we can calculate FZ, as you will see. It's related back to the total fluid force, PGA, and the angle of inclination, the geometry of the system. We know that. But we don't know FPZ. And going to the X component, that doesn't help us get FPZ. So you could start here, but the problem is you wouldn't be able to solve the problem. Again, what are we looking for? RA. So on the bottom of the slide, you can see that if we do a moment equilibrium, taking moments about point B, if clockwise is the positive moment direction, RA if it were allowed to continue, would create a positive moment about B, and it's got a moment arm M. Remember, the moment arm is the distance perpendicular from the line of action of the vector.
We have a question about what is L.
L is, I'm going to get to. So M is the moment arm for RA. And then because you took moments about B, FBZ and FBX cancel. Their moment arm is 0. And then the only other force which is creating a moment about B, you could certainly look at the X and Z components about it, but you might as well just take F total. And its moment arm, again, if F is perpendicular to the surface, L is the moment arm of F. It is the distance basically parallel to the y-axis from F to B. And if you look at this, we can solve this equation for RE. And when we solve it for RA, look at the three terms you have there. F, that's the force on one side of the surface. That's PGA. M is going to be related to the geometry of the system. Sine or cosine of the angle times, the hypotenuse, the length of the gate is 8 feet. L is the distance from the force to B. It's parallel to the y dimension. L is going to be related back to the center of pressure. So, again, we know that the vertical height of this gate from the inclined axis, its total length is 8 feet, but in the vertical, it would be 4 feet. And likewise, M is going to be 8 foot cosine 30. So remember, this surface is inclined at 30 degrees off the horizontal. So that's where we got that from. That was from the definition that we had in the original slide. This surface is inclined 30 degrees. So right now, what you know is M in this last equation. F we're going to find from fluid statics. L we're going to find also from fluid statics, both from forces on submersion. So at the top of this slide is the same equation we ended with. What we're trying to solve for is RA. The only equilibrium equation in which RA explicitly jumped out at us was not from force equilibrium, but moment equilibrium. The other temperature? Yes. So the fluid force F is from forces on surface. The moment arm L for F is found from the location map, YCP. We're going to sketch this for you. And then the moment arm for RA is from the geometry. That was M. So basically, these three bullets are addressing the three terms we have in this equation. So for the force, that's equal to the pressure at the center of area times the area. G, if you remember, I sketched this surface for you. It's 8 feet along the y-axis, 6 feet in the paper. G is located vertically. Remember, the top of the gate is 18 feet along the y-axis, 9 feet vertically to the top of the gate with beams. If we were looking in the vertical dimension, H bar, the vertical distance from the free surface. So here's our gate, here's the free surface. And your G is here, and this is H bar. H bar is the 9 feet to the top of the gate, plus the force on theta. So the other way to look at this, again, one is vertically, one is along the y-axis. We developed F is equal to PGA. By looking along the y-axis. So we're going to calculate an H bar. I'm just showing you there's a lot of ways of getting the same answer. And you should use whichever method is comfortable for you. You can work in the vertical domain, that's the H-axis. You can look in the inclined domain, y-axis. You will get the same answer. If you don't, you did something wrong. So B, again, is the point at the top of the gate. So B is here. And it's located, again, 18 feet below the free surface along the y-axis. If the gate is 8 feet long along the y-axis, then along the y-axis, y bar is the 18 feet from the free surface to B, plus half of that 8-foot length, 8 foot over 2. That should be equal to 8 over 2 is 4 feet. Okay? So if you look at the equation at the top, it specifically applies, look it up in the back of the book. We just computed h bar and y bar. Theta we know, and the area we know. The area is 6 foot by 8 foot. So either way we go, we can calculate the force. Again, h bar is y bar sine theta. We just found that y bar is 22 feet. I'm just showing you a check at the bottom. The second bar, the second bullet, we showed that h bar is 11 feet. And again, if you worked in the y domain, you can still always go back to the h domain to get the same answer. So, pressure at the center of area, gamma y bar sine theta, which is gamma h bar, and that's 686 pounds per square foot. That's PG. And then obviously the force on the submerged area is now that pressure times the area, 6 foot times 8 foot squared. If we used instead of the pressure at the center of area, the fundamental equation, F is equal to gamma y bar sine theta A. Here it is expanded out, and we get 32,900 pounds. If you had used the vertical dimension instead, 32,900 pounds. Okay. And remember, this vector is perpendicular to the surface. So the surface is 30 degrees off the horizontal. The vector is going to be 30 degrees off the vertical. We know it's geometry. It's not imaginary. Great. So we had this equation where RA, it probably is on this slide. I don't remember everything now. RA is equal to F L over M. That was our equation for moment of inertia. So here is the system again. And what we have is this 8 foot by 4 foot gate. It's the red in the diagram. We're after RA. And the moment equilibrium gave us the equation that I just put in the right hand side. This is our force F. We just calculated it, 32,900 pounds. It's got a moment arm, L to D. How do we find that moment arm? Well, we can calculate YCP to the free surface. That's how the YCP equation was developed. The distance along the y-axis from the center of pressure to the free surface. We know the distance from the free surface to the beat is 18 feet. So L is YCP minus 18 feet. Okay. Oh, yeah. All right, so that's what we just determined. The moment arm, the last piece of the equation we have F and we have M, just need M, is YCP minus 18 feet, and this is measured along the y-axis. YCP. This is the equation I started off with today. This is the equation we developed 2 lectures ago, and we used last lecture. The distance along the y-axis from the center of pressure to the free surface is the moment of inertia metacentrally. In this case, we have a rectangle. The moment of inertia of a rectangle is 1/12 bh². In this case, the b in that moment of inertia equation is the dimension into and out of the paper. The h is the dimension along the h-axis. Divided by y bar a plus y bar. And everything in this equation is done. So again, in the IX formula, b is the dimension of the screen, and in that same formula, h is the dimension. Unfortunately, it's the same word. H is not the same h as the vertical dimension, but I'm trying to be consistent with what's in your book and use what they have in your books. So we have everything in that equation to calculate this. So 112B is 6 feet, H is 8 feet, that's cubed, divided by Y bar, we know that's 22 feet, times 8. Area is 6 foot by 8 foot or 48 square feet, plus Y bar. So the first term is 0.24 feet, the second term is 22 feet, so YCP is 22 feet. The center of area, Y bar, is at 22 feet. Along the y-axis, YCP is lying below Y bar. Center of pressure is always out of below center area. So we would subtract off 18 feet, and that would give us the moment arm of the resultant force F, which is the resultant force of the pressure distribution of the fluid on one side of that cube. That moment arm is 4.24 feet. And then when we look at the development of the problem, the equation which we had developed from the moment equilibrium was that RA is FL over M. That came from some of the moments about B is 0. So we have F, that was the 32,900 pounds, whether you went along the H dimension or the Y dimension. We have the moment arm L, 4.24 feet, which again was found by knowing where the center of pressure was. Whenever you're doing a moment equilibrium and you have to use the force of the fluid on the surface, moment equilibrium dictates that you have to know where that force acts. That force acts at XCP, YCP. You have to use that equation. The moment arm for the resultant force of the fluid on the surface is always somehow related to YCP. And then M, a long time, we calculated that M was equal to the 8-foot cosine of 30 degrees. Did I not solve that? No, 20,200 pounds. So again, what you have basically is this force was 32,900 pounds. This force is 20,200. And again, you can calculate the X component and the Y component of that force F if you wanted to find FBC and HX. Ultimately, you would, because structurally, you need that pin connection to stay in place. And similarly, whatever you're designing down at this location, it needs to be able to accommodate that force or that stress. Take that force over the area of X, and it's a stress. Again, now you have the information how to design. If you were looking at that resultant force and where it acts laterally, again, what we have is this rectangle that's 6 by 8. 6 feet by 8 feet. And the center of area is right in the middle, and along the y-axis, it's 18 feet. From the free surface down to point B at the very top of the gate, 22 feet down the center of area. But again, if we put our y-axis right through the center of area, then the product of inertia, IXY, is 0, and all that says is that the location of that force is right below the center of area along that y-axis that we drew through the center of the area, because that y-axis through the center of the area is an axis of symmetry. Great. So, at the very, are there any questions on that? I can go back to certain slides. So, basically, I'm going to do the same example, but it's a different gate. I want to use different numbers. But what I just left you off with was we could calculate the X and Z components of the resultant force on the planes of each surface. So here we have a gate that's inclined 60 degrees off of the horizontal surface. The free surface is vertically 2 meters above the top, and this gate is 3 meters along the inclined axis and 10 meters into an outer paper. So again, the top of the gate is 2 meters below the water surface. And if I go back, this 2 meters is 2.3 meters along the y-axis. And that's what I had in the presentation. Oops, I had sign. That should be good. No, I'm wrong. Sorry. So we can get the geometry of this gate. Remember, the gate itself is 3 feet along the Y, 10 feet in the paper. If the gate is 3 feet along the y-axis, we have 2.31 meters of free surface to the top of the gate. To get to the center of area, we would add the distance from the free surface down to the top of the gate, plus half of the 3 meters to get to the center of area. So the center of area, this is y bar, is 3.81 meters below the free surface. It's along the y-axis. And what we would then say is the resultant force of the fluid on one side of the surface is PGA, which is gamma y bar sum theta A. So in this case, if we have water, specific weight of water, 9,800 newton per meter cubed. Y bar, 3.81 meters. Sine theta, sine of 60 degrees. A, 3 meters per 10. So filling it all in, that's what we have. And that means what we can then do is calculate that we have the force of the water on one side of this 3 foot by 10 foot gate is 980,000 newtons. I said 170,000. That's pretty simple. And the last problem won't be labored all of these calculations. But again, the more you do of these, you can see it's pretty straightforward. You do the geometry first, and then you do the calculations. So, this. So if we look at the resultant force now, it is a force which has, this is our force we just calculated. And we can subdivide it into horizontal and vertical components. Now, to do that, all we would need to know is the force triangle. So again, if the axis is 60 degrees off of the horizontal, we can identify that it's a specific geometry off of the vertical. And then knowing that, we can get a right triangle. And from that right triangle, we can calculate the horizontal and vertical components. So with this right triangle, if the hypotenuse is our resultant force, 970,000 newtons, then horizontal component is F sine 60. And remember, because of the direction of the total force, it has to have components in these directions. Never forget the direction. So we can get the horizontal component from the force triangle, sine of 60, vertical component, cosine of 60. And you know from Pythagorean theorem that the magnitude of a resultant vector is the horizontal square plus the vertical square of the square root. And if you do that, you get 970,000 newtons, as you should. So all we did was we used F is equal to PGA to get the 970,000 newtons. Then we just used the force triangle to calculate the components. In your notes, write these two down. 840,000 horizontal, 485 vertical. Because now I want to look at another way of calculating them aside from PGA. Question?
Yeah, it's wrong with geometry, but should we keep the 30 degrees at the top the forces?
So sine is opposite. Actually, these may be reversed. I think you're right, but I think they're reversed.
Oh,
It's 60 degrees off the horizontal, so it should be 60 degrees off the vertical.
okay, thank you.
Problem is, I gotta make that correction, I hope I remember. To go back. So, yeah, switch those two. Thanks for picking that up. So, one way of looking at this result, of course, is if this is our surface, okay, if this is our surface, basically over this 3 meter by 10 meter surface, so this is 10 meters into the board, it's kind of showing you this. What you have is in this shape, this is the pressure prism that is acting over the surface. It's the pressure at the top is gamma H1, and the pressure at the bottom is gamma H2. And since it's changing linearly, F is equal to PGA is basically PG is the average pressure from the top to the bottom because it's a rectangle. And so what you're doing is gamma H1 plus H2 over 2 times A. And if you look at all of these terms, H1 plus H2 over 2 times A is the volume. Sorry, gamma times A is basically the volume this pressure prism occupies. So fundamentally, the force is equal to the volume of the pressure prism. This makes it any easier to comprehend. Over any submerged surface, there's a pressure distribution. That's what I'm calling the pressure prism. And if you can calculate the volume of that pressure prism, you basically have the force. Just another way of looking at it. So what I'd like to do is break the resultant force into components and actually start off by calculating the components first. I want to, before we would calculate the total force, F is equal to PGA, and then break it into components. Now I want to calculate the components first, and then come up with the total force. Same problem, just to show you that you get the same answer, but more importantly, there will be some problems where you only care about the horizontal and vertical component. And that's what you need to know. When we get to the end of this fluid statics business, we're going to look on forces on curved submerged surface. That's when we're going to need to move components as well. So, if we look at this, the horizontal component of the resultant force, I'm telling you, is acting on a projection of that inclined surface into a vertical plane. Now I'm going to sketch for that. So, to project our inclined surface into a vertical force, this was our inclined surface. It was inclined at 60 degrees. It's a 3 meter by 10 meter gate. And if I just draw dashed lines, and this is a vertical plane, all I'm doing is think of this as shining a flashlight onto that surface, and you're looking at the shadow on the wall. The wall is a vertical plane. And so if you have a rectangle on an inclined surface and you shine shadow on it, it's a rectangle on the wall. It just doesn't have the same dimensions anymore. Its dimensions are going to be the vertical dimension, which is changed, by the horizontal, which is unchanged. So whereas the real inclined surface is 3 meters by 10 meters, when I project it into a vertical plane, it's a rectangle that's 2.6 meters high by 10 meters into the okay? And now what's happening is, if you think about it, from the vertical surface, we have a pressure distribution, and that pressure distribution is changing linearly over the surface. And this is the pressure distribution of the horizontal projection. Let's call that AH. It's a horizontal projection of the area. And so by doing this, what we can do is calculate the force on the projection, and that gives us the horizontal complement of the overall resultant force. So again, it's originally 3 meters by 10 meters, projection is 2.6 meters in the vertical direction by 10 meters horizontal. So, just as we did before, in this case, the force on the horizontal projection is equal to the pressure at the center of area remember that projected area is 2.6 meters high. So again, it's a rectangle, and we know exactly where the G should be for the horizontal projection. Same equation, it's just that we're looking at the projection. So the distance vertically, because we're looking in a vertical projected plane, the distance vertically to the top of the gate is 2 meters. The distance to the center of area, if the gate at 3 meters projects into the vertical is 2.6 meters, then the center of area is the 2 meters down from the free surface to the top of the gate, plus half of the length in the vertical, 2.6 meters over 2, to get to the center of area. So this is getting us basically h bar, a vertical distance down to the center of area. When I multiply this by the specific weight, gamma h bar is PGH. That's the pressure acting at the center of this horizontal projection. And then we're multiplying that by the area. And again, in the projected sense, it's got 2.6 meters high by 10 meters forward. What do you get? 840,000 newtons. That's the exact same number when we look at the force triangle, right? Coincidence? So again, this is another way. This is what we're going to have to do for curved surface. Okay. Does everybody understand this? It's really not that complex of a concept, but again, I've been doing this for so long, maybe it's.
What's like the mathematical
So we're converting.
Oh, that's
We're converting the which is along the y-axis into a vertical dimension.
Yeah.
So another way of looking at this again is because you have a linear and plane changing pressure distribution on this horizontal projection, you can just average the pressure at the top, gamma times 2p, plus the pressure at the bottom, gamma times 4.6 meters, so gamma 2 meters, 4.6 meters, average that pressure, and you get the same number, 840,000. So we have the horizontal component. Now we want to look at the vertical component. And again, think of the surface itself. We just want to think of the pressure distribution. Remember, pressure is a scalar. It acts the same in all directions. So all we're going to do is reorient the pressure distribution to be acting vertically on the surface. Okay, so this is our real system. This is the inclined surface. H1 we've identified is 2 meters. H2 is 4.6 meters. We've already done these calculations. If this is our real inclined surface, I'm just rotating it horizontally. It's not horizontal, but that's all I did was rotate it. So again, we've got gamma H1 to gamma H2. So basically what's happening is you have a linearly changing pressure distribution that's acting, again, we're looking at just vertically on the surface. And if you think about this, this is going to have a dimension in the x by 10 meters into and out of the paper. And you have a linear change in pressure distribution. So we can calculate this vertical force just by looking at the average pressure over the area. Same thing as we did in the horizontal case. So again, going from one side to the other, we've got a depth of submergence at the top end of the surface of 2 meters, a depth of submergence at the bottom of it is 4.6 meters. And if we projected this into a horizontal plane, because we're looking at pressure being perpendicular to the projection, we have an area of 1.5 meters, 10 meter width. So here we have the average pressure. And that's our PG. That's the pressure in the center area of this horizontally considered surface, which has a horizontal distance, 1.5 meters, 10 meters. And when you do the calculation, 481,000 meters, the same thing we found before. So that may look a little abstract, so I want to make it even easier for you. If you look at what we did here, .6 meters is physically the depth of water above the bottom of the surface. Two meters is physically the depth of water above. 4.6 meters plus 2 meters over 2 times the area is physically the volume of the pressure, or the volume of water above the surface. So the vertical force is the weight of water above the surface, which makes a lot of sense, doesn't it? And that's all you really have to do is, we had an earlier homework problem where we were trying to calculate the volume in a trough. And the volume is equal to, in that particular case, it was the weight divided by the specific weight. But basically weight is equal to specific weight times volume. So for the vertical component of the force, you're just calculating the weight of the fluid above the surface. Question.
Is there like, what's the difference in labeling volume like that, like the upside down A versus the gradient?
I try to do it to distinguish all the different V's that we're going to see in this course. So for volumes, I usually put a line through it because there are a lot of V's in this course. Velocity will be one of the big ones coming up. So horizontal component of force, we calculate by projecting the surface into a vertical plane. And then the vertical component is just the weight of the fluid above. What if, last minute, what if you don't have fluid above the gate, you have fluid below the gate? Is there still this pressure distribution acting on it? Of course. The vertical component of force is calculated the same way, it just acts in a different direction because now it's a buoyant force. It's pushing up. So basically, you're looking at the fluid that would have been displaced or which would have been above the surface. These surfaces are infinitesimally thick. So again, if the fluid is physically below the surface, so let's say we had a tank that looks like this. And this is the gate we're looking at. Basically, there's no free surface here, but you have this pressure distribution acting perpendicular to the system. And it's going to have a resultant force, which is going to have a horizontal component and a vertical. The horizontal component, again, is found by projecting into a vertical plane. The vertical component is the weight of the fluid that would have been above the surface. And because you're displacing the fluid, its action is upward. It's a buoyant force. I see I'm out of time. We'll try to do an example of that. See you next class, Monday, through the weekend. 4 weeks out, I can't believe it. It's still here.
What happened to the laptop?
I have no idea. This is what's going on.
Just today?
So last night when I got home, I was watching TV, I was having my dinner, and it wouldn't turn on. And then I was like, wow, it's really dead, like that's the problem. And then I literally have no